Visible light spectroscopy. So during this lab, we measured the different peak absorbances of visible light, and we used mainly their wavelengths, but also their peak absorbances, to figure out what color this unknown ink we were given was. For example, to start off with, when we measured yellow, we found a peak absorbance of 0.451 at wavelengths of 416.8 nanometers, which makes sense as if you look at the color wheel, 416.8 nanometers falls under the violet, or in this case purple, or violet or purple wavelengths. And if we absorb, or if the ink is absorbing those types of wavelengths the most out of all wavelengths, then the resulting color we see reflected into our eyes is yellow. So the yellow ink will have a peak of absorbance of whatever color is opposite it in the color wheel, which in this case is violet. And this is true for all colors. For example, you'll see both the blue and the green ink had peak absorbances at wavelengths of 628 nanometers, although they differ in decimal points, because 628, if we look at the table below, is between the values of red color, or red wavelength, but is also very close to orange. And orange and red are both directly opposite of blue and green on the color wheel. So if those get reflected, the resulting color is blue and green in our eyes. Orange has a peak of reflection of 481.9 nanometers, or nanometer wavelength, which, if we look below, falls under the cyan wavelength, and directly opposite is orange. Purple was a bit strange. We'd expect our results to be a little bit higher, as we got a peak absorbance at 525 nanometers, which falls under green. We'd expect it to be under yellow, since yellow is directly opposite of purple, or at least high green, since it would be closer to purple, or closer to yellow wavelengths, so the result would be purple. But we got 525, which isn't completely unreasonable, since we see some of the lighter greens would still fall under the purple, or purple-ish, but we'd expect to see it a little bit higher. And black falls under the 409 nanometer wavelength at peak absorbance, but you'll see the peak absorbance is actually 3. This is because black absorbs all the light, or all light wavelengths, since black is the absence of light, and by absorbing all of the light, the visible color we see is black in our eyes. So to find out the unknown ink and what color it was, we measured the peak absorbance and its wavelength, which came out to be 0.761 absorbance at wavelengths of 391 nanometers. If you look at the table, 391.3 nanometers falls under the violet wavelength. And since it's quite a low wavelength of purple, we can assume, because orange is absorbed at much higher wavelengths, as we see in our results that were absorbed at 481, we can assume that it goes on the opposite way of the color wheel, which would be towards green. And so the assumption, or we can determine that the unknown ink is some color between yellow and green, which would be chartreuse, or we can just say yellow, but more towards the green side of yellow. We then used lime cordial concentrations and peak light absorbances to figure out an unknown lime cordial and its concentration. So firstly, we measured the peak light absorbance of different concentrations of lime cordial, and we found that at 20% there was a peak absorbance of 0.114. At 40% it had a peak absorbance of 0.262. 50% had a peak absorbance of 0.304, and so on, until we had just lime cordial, fully concentrated. And we plotted it against the graph with a line of best fit, and we found a linear correlation between the concentration and the absorption. After measuring the unknown lime cordial, we saw a peak absorbance of 0.643, and using this and the fully concentrated lime cordial, we can divide the unknown lime cordial absorption by the fully concentrated lime cordial absorption and get the percentage, and figure out as a percentage, which is 93.4%, which is in accordance to our results, as we see between 0.6 and 0.7 absorption would fall somewhere between 90 and 100% concentration.